Okay, before we start, maybe we can have some review on Monday class. So the feedback time, we got the questions, the tangent inverse. And it should be 1 plus x squared, not 1 minus, so it should be false. And yeah, most of you got correct answer. And I think this tangent inverse here is quite important. So whenever you have the tangent inverse, you can directly take the 1 over 1 plus x squared. Okay. And then the other question, the second question is you have the functions and you need to evaluate the derivative at x equal 1. So first, finding the derivative, you have ln. And the first thing you need to do is, this is the inside functions, right? This is the outside function. Or let me write here. So outside. Okay, code. Okay. Go back here. This is inside function, outside functions. So this is the outside function is x plus ln x, and you will get precisely this, and this will be the chain rule. And evaluate at 1, you get 2. Okay, I think it should be okay for you. Okay. Now we have the third question. We have a function or curve. And the question is asking at what point that the curve will have a horizontal tangent or tangent horizontal. Okay, first, the idea is to derive, okay, to find the derivative. This is the first derivative. And then horizontal is when the slope is 0. Slope is equal to 0, or y prime is 0, or the first derivative is 0. So we need to equal this whole thing here, the first derivative with 0 here, okay? Okay, by doing this, the one that make the whole equation become 0 is the numerator, right? This is the numerator. So we can focus on the ln x plus 4, okay? So we can take this ln x plus 4 cube equals 0. But to make it 0, we just focus on this x plus 4, right? The ln that equals 0 is ln 1. So we need to make it x plus 4 is equal 1. Okay, and then we get x is -3. And then we check the y coordinate is 0. So that will be our answer, this or this. Okay. So yeah, congratulations for the winner. Okay. Okay, I hope no problem with the feedback questions. Okay. Now we are still in related rates 3.9, and I will give you maybe 1 or 2 questions more example, and then we can move to 3.10, the linear approximation. Okay, and I hope I can finish linear approximations by today, and we can start next Monday with the new chapter, chapter 4. Okay. Okay. Now still the still example. We still have this 2 example now. example 4. This is the questions about you have a car traveling west. Let me draw a car. Okay, traveling west. Oh, wait. Here. Okay, this is the QR code. Okay, have you finished? So for those of you who are just coming, maybe coming late, scan the QR code. Okay. Right. Let's move back to the example 4. Okay. So this will be the car A. Let's say this is A. And the other car, car B, traveling north. Let's say here, because both of the both cars will have an intersection later, right? So let's say we have B here. Okay, and let me draw the line, the rest of the line. Okay, and let's say we will have an intersection at this point C. Okay. Okay. The questions is what rate are the cars approaching each other? So the question is when both cars approaching. So maybe it's going to go here. The A is also going here. So you want to know the rate when the cars is approaching each other. So which means between this A, B, there will be a line here, right? The distance between A and B. The distance, let's say the distance is, if this is X, this is Y. Let's say this is Z. This is Z. Okay. The distance Z will change every time A and B move, right? So I believe that that rate of change of the distance Z will be our final goal. Okay, so uh, we need to find the dz/dt, because the question is requesting that finding the rate of the cars when they both approach each other, when car A is 0.3 miles and car B is 0.4 miles from the intersection. So we need to find the uh, where this is 0.4, this is 0.3. We need to find this rate, the ZDT. Okay, so we will have a triangle. At least it looks like a triangle. Okay, so by doing this, we get this is X, Y, and Z. So we know that because of this triangle, we know that this is the fact that we can use the Pythagorean theorem, and then we can find the derivative with respect to t, dt. So it will be dz dt. Okay, we got that. So dz dt is, I will cancel all 2 here. So this will be 1 over z x dx dt plus y dy dt. Okay, that's our formula now. Okay, so this is x equal 3, this is y, and then z will be, we will have 0.5 by Pythagorean. So we can write down the number. This is 1 over 0.5. This will be 0.3, and we know the dx dt here. Dx, let me, this is 50, dy dt is 60, and because in my preference, because the distance x is decreasing and distance y also decreasing, both of the dx dt and dy dt, I will put negative on it. Okay, so I will put the negative. This will be negative 50 plus, well, if you put positive, both positive, that's also okay. It depends on you, as long as it's consistent from the first definition you have, and then calculation, all still consistent, you will get the same answer and the same conclusion. Okay, you will get, this is negative 78 mile per hour. This negative means that the cars, both cars approaching at a rate of 78 miles per hour. Okay, let me give you a few minutes to check, and then to read the whole answers. Anyway, whenever you feel you need time to write or to take notes, and maybe I forgot to stop, you can chat in the box. Okay. Negative. Okay. Negative is because I make a definition for negative for me. Okay. So if this is x, okay, this distance x, okay, distance x is decreasing, right? Because the car A is moving to C. Okay, so I make the distance x decreasing. Okay, and then distance y also decreasing when B is moving to C. Okay, because it's decreasing, I will make a definition for the rate of change negative. Okay, so that I put negative here and negative here. And if the answer we get also negative, so this means that my definition is that because it's decreasing means the car A and car B both are approaching at some rate, right? The rate that we have calculated is 78. Well, it doesn't matter if you are using 0.3 and then but just positive like that, all positive, and you get the answer positive. Different answer like this, it doesn't matter. It's okay. It's okay. Because in here you just say that, okay, I will make both cases positive, and then you know that when you get the result positive, you have the same conclusion that, okay, the cars both are approaching at this rate, at this 78 rate. Okay. I hope you don't mind a positive, negative. Okay. As long as you make the definitions at the beginning the same as when you are having the end of calculations, you get consistency. That should be okay. Should be okay. But for me, usually I like to have, if I have some distance that is decreasing, I will take that as a negative rate. Okay, because the rate is making the number decreasing. Okay, if it is increasing, I will take that as a positive. All right. Okay. The next question, the example 5. I hope you also try. I already give this, I think, last Monday. I hope you try by yourself to check whether you at least understand the question first. Okay? At least. Okay. Okay. Now the example 5. You have a man. He walks along a straight path at a speed of 4 feet per second. And a spotlight is located on the ground 20 feet from the path, and focus on the man. So keep focus on the man. So you have a spotlight. The spotlight is basically a lamp, right? A lamp that can mark, or usually if you see any performance in like a singer, and usually there will be a light that is focusing on only to the performer or the singer. That's the spotlight. So the man I will draw here. He walks along the straight path. Let me draw. Maybe this is the path. Okay. And then he walks. Let me go. He walks. Let me draw the second man. Same man. Okay. Yeah. Okay. Okay. Now, from this path, we have another case, which is we have uh, the light. Let me make the light with blue. So the light, it can move or it can rotate. Okay, the light can rotate. So it can rotate like or going to the left also. Okay, right? So the light can rotate to the left, the right, and it is focusing to the man. So let me. Okay, let's say that is that's the spotlight. Okay, so that's the spotlight. Okay. Okay, let's name all the point here. This is 20 feet, always 20 feet, because the spotlight is fixed on that point. You cannot move the spotlight. It is rotating but not moving, right? So it's always 20 feet. And let's say we have X distance here, when the distance that the man traveled, the man walking, let's say it's X, okay? And you know that the X over dt is 4 feet per second. That is the speed of the man. Okay. And then because of the spotlight is rotating, if we draw a triangle, this is 20, this is x, okay? And if we take this as at an angle like that, we know and we can make a correlations between these three terms. We can take tangent theta as x over 20. And we can make it x equal 20 tangent theta, right? Because the question is asking what rate is the spotlight rotating. So if we are going to differentiate this with respect to t, we will get dx dt. We know dx dt from the question, 4 feet per second, is equal 20 secant squared theta and theta over dt. So this is the questions that we are looking for, or this is the one that we are looking for. So this is asking dt over d theta over dt. And move here. So we get d theta over dt is 120. And then this is cos squared theta, or 1 over secant is become cos squared. And then dx over dt. So cos theta, what is cos theta? We know that from the questions, we need to have 15 feet. Okay, so cos theta will be, if this is 15, okay, the other one is 25, right? So 15 squared plus 20 squared is 25 squared. So we have 25 for the hypotenuse. Okay. So cos theta will be, let me write here. So it will be 1 over 5 because the SDT is 4. 4 over 20 is 1 over 5. Cos theta will be 20 divided by 25. And this will be squared. Let me make it simple like that. So d theta dt will be 16 over 125 radian per second. Okay, this will be the answer. All right. Any questions? Do you want to ask? Yeah, we can use also. We can use because sometimes if you read the angle problem, we can also use the inverse. Okay, you can you can see sometimes it's better to use the arctangent sometimes, and sometimes you can just use directly like this. It's fine as long as you got the right directions. I think you can also use the tangent inverse if you want. Okay. But yeah, read the questions carefully. Okay. Because sometimes maybe if you take the arctangent, maybe it will be taking you circle and then maybe take it longer sometimes. Okay, the problem with the tangent inverse is when you are dealing with this. Okay. If you take the tangent inverse, well, you will get the tangent inverse something x over 20. Well, you get directly, right? But as long as you don't mix up with the original tangent, so tangent inverse, so you have 1 over 1 plus x over 20 squared, and then this will be dt over d theta. Uh, this will be having so let me write here dx over dt. Yeah, I think it should be okay. Okay, it's up to you actually. Up to you. And you can check which one is easier when you are looking at how the structure will be. If you think that well maybe the structure is easy when you use the arctangent, you can use the arctangent, or if not, then just use the. But actually, it's up to you. It's up to you. Okay. Any other questions? Okay. If not, then I think I can take you to maybe one or two more example. Okay, this is I think the first five example that I tell you that I told you also in the Monday class. I think five of them are basically like basic type questions in the related rates, and from there, actually, we can have more variations in the questions. But ideally, usually it will be like having a triangle using Pythagorean, trigonometric. Um, if it is like a geometric, like area, volume, you will have a change in area, change in volume, something like that. And also in triangle, not only Pythagorean, we can also have something like a law of cosine. If you remember cosine, law of cosine, or maybe law of sine. I think law of cosine more ideal in the related rates problem because it has sides and the angle. I will show you later. Maybe we will have an example about that. Yeah, I think we can move on to the next example. Okay, let us start from first one is a plane flying with a constant speed of 300 kilometer per hour, pass over a ground radar station at the uh, altitude of 1 kilometer, and then climbs at angle of 30 degree. And then the questions, the what rate is the distance from the plane to the radar station increasing? So to understand what kind of distance and how it's going to increase, we need to at least draw the diagram. Okay, draw a diagram. So let's say we can draw the, or let me give you a few minutes. You can try and then check by yourself how it is, and then maybe after a few minutes I will show you how, and we can compare our results with is it similar or maybe a little bit different. because sometimes maybe the process is a little bit different, but the answer is okay. Sometimes we can have 2 or 3 ways to work, but I think that is not a problem. Calculus or mathematics in general, we don't have um, really exact solutions. At least there will be 2 or 3. I think that's okay. That's the beautiful thing in calculus. You can work as long as you like. Okay. Um, for example, you prefer maybe changing the algebra first, and then you finish with the calculus, or you directly go to the calculus solutions. Uh, that should be okay. Depends on you which you are more preferable to do. Okay, for these questions, if you take a wrong diagram or wrong sketches for to connect the plane, the height, and the angle, you will get a different conclusion. Different conclusion. Okay, first we need to set up our mind and look at the questions. Okay, so a plane, it has a constant speed. It's flying. It has constant speed. It passing over the ground radar station. So maybe let's draw the radar station. Maybe the station here. That's the radar stations, right? It has, yeah, usually to detect the object, right? And then we have a plane is going to pass over. Let's say the plane is here above the radar station. Okay, so passes over at altitude of 1 kilometer. So let's say um, we are having the altitude here. Altitude means height. Okay, something that you might, I think, possibly heard when you are dealing with a flight, a plane, right? When you are inside a plane, you'll notice that maybe the pilot will say, "We are blah 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 altitude, some kilometer," right? Okay, so this will have 1 kilometer altitude, so it's quite nearby in terms of airplane, right? And then, or maybe I will make it a little bit lower, maybe here. Okay, and then passing over and then climbs at 30 degree. Okay, climbs. Maybe I will get there. So climbs means maybe 30 degrees here. Okay, so this will be 30 degree. So this is climb at that 30 degree. So the plane will be here. Okay, we'll be moving to here. This will be the plane. And then what rate? The distance, the plane, and the radar. The distance. Okay, the distance is from here to here. Okay, that's the distance. So if we want to draw simply, then we can draw. We have that. Okay, that's the triangle we have. Okay, or maybe here. Okay. So this 30, then the whole thing here would be 120 degree, right? 120 degree, the angle. This is 1 kilometer. And then this is, let's name all the distance. This is 1. Maybe this is x, this is y. Okay. Okay. Now we have maybe just one to make more clear. 1 x, y, and then 120. And maybe I will erase the 30 here. Okay. So like I said before, if we have triangle, we have sides and then we have angle. Maybe we have the law of cosine. I hope you still remember on what is a law of cosine. So law of cosine, or let me write here in more general. Uh, let's say that is our, let's say this is A, B, C. The angle A, angle B, angle C. Or usually you will have a alpha, beta, gamma, or beta. I will just use ABC to make it simple. The law of cosine, let me write what the law of cosine mean. If you want to calculate A squared, this will be B squared plus C squared minus 2BC cosine the angle. If you want to calculate B squared, this will be A squared plus C squared minus 2AC cosine B. You have C squared, you have A squared plus B squared minus 2AB cosine C. And if you are maybe wondering how the law is possible, we will have a lot of time to deal with. But let's say this is the law of cosine. Okay, I will just give it just as it is. So we can use this expression in our case here. Okay, so we have x, y, 1 as our sides, and the question is actually this y, right? This the distance here, dy over dt, right? We are going to find dy over dt. So let's say we have y squared is equal that will be our equations by the law of cosine. And then we can calculate the cos 120. This is negative half, right? This will be x squared minus minus of plus x plus 1. Okay. And what's the next move? We differentiate with respect to t to find the dy over dt. This will be 2y dy over dt equal 2x dx over dt plus dx over dt. Yeah. And then dy over dt will be, this is 2x plus 1 dx dt. This will be 2y, right? Okay, now we are going to check all the symbols here. What is x? We can find from, we have dx over dt is 300, right? The question is asking a minute later. Okay, so 1 minute later. We know that 1 hour is 60 minutes. So 1 minute later, x will be 300 divided by 60. This will be 5 kilometer. So this will be 5. X will be 5. And how about y? we can use the law of cosine here. So y will be, let me write y will be square root of 5 squared plus 5 plus 1. This will be, yeah, this is not really good number here. Square root of 31. Okay, we can check with the result. So dy over dt is equal to, or this will be 11, yeah, 11650 kilometer per hour. Yeah, that's it. Okay. Okay, maybe the thing that maybe you are familiar with the law of cosine. If you see the triangle, the law of cosine triangle is more random triangle, right? As long as you know the sides and one of the angle. But if you have maybe right triangle is the triangle with the 90-degree like that. If you have the right triangle, it's much more easier if you use the trigonometric, right? Trigonometric inverse or the just regular trigonometric. I think that will be better. But because you have a random triangle, not really right triangle, then you need to use the law of cosine. Okay, any questions? Okay. Or maybe let me give you one more example. One more example. One more example. Let me go through. Wait. Then lighthouse. Okay. Oh, okay. Okay. Let me give you another one. Okay. So I hope you already take notes from this one. Okay. And remember, I think because we will finish chapter 3 today, I will compile the notes of my notes, chapter 3 notes, and I will upload in the Google Classroom. And yeah, you can check my notes if you want to review some sections. And because we finished chapter 3, hopefully by today, so maybe next week or next 2 weeks, I think next 2 weeks, I will prepare another quiz, only chapter 3. you need to find out on Google Classroom. So you need to check periodically. But I will also announce on the Moodle in which platform we will have. Okay. And please read the descriptions carefully. What you need to do, what is the requirements. Okay. Okay. Next, let me make a new one. Let's say this is the questions now. Okay, yeah, I will cover the question on related traits that is not being covered by the examples, or maybe it's similar but it has some variations. Well, let's try this one. A lighthouse is located on a small island 3 kilometers away from the nearest point P. So you have a lighthouse. The distance is 3 kilometers from the P. On a straight shoreline. Shoreline is like the beach. You have a border between the beach and the sea. That's the shoreline. And the light from the lighthouse makes 4 revolutions per minute. 4 revolutions. So 1 revolution is 1 circle. Okay, 1 circle. So how fast is the beam of light moving along the shoreline when it is 1 kilometer from P? It seems so first you need to understand first how it works, how it works. Okay. So I think it's better if you imagine the lighthouse like if you see the movie, there is like a lighthouse. Let me draw the lighthouse. Is it like that? Not sure. Maybe it might be like that. Maybe not really like this. Maybe like that. And it has, it can rotate, right? It can rotate. And it has the light. It can rotate, right? So let's say, let me draw again here. So let's say this is the lighthouse. And let's say this is the point P that is the nearest point. So this is the shoreline. So the point P is 3 kilometers away. So let's draw the 3 kilometers here, 3 kilometers. So like I said, this will be rotating. Okay, rotating. Okay, so you are seeing from the top. Okay, seeing from the top. Okay, and then how fast is the beam light moving along the shoreline? So this is the shoreline, the blue line here, the blue at the bottom. So it will be moving along. Okay, I hope you get the idea how the questions works. So we can take this as a simple triangle. This is P, this is 3. Let's say this is X, okay? The one that we are going to check, okay? That X, and then because it's moving, or not moving, because it's rotating, the lighthouse is rotating, the lamp, I mean, so it has some angle that's rotating. Okay. So if you get this, okay, this idea here, rotating, and then you get this triangle here, it's really helpful because after this, I think some calculations, right? And then in related rates, some calculation is just a short calculations. The important thing is how to make the schematic or the diagram. Okay, now yeah, the questions is asking the dx over dt, right? How fast the beam light moving along the shoreline. So at this x, there will be a light that is moving. It's We can define this as dx over dt. That is we are looking for. So we have theta, we have x, we have 3. I think we can just use the tangent. Right? We can use the tangent. We can take this tangent. Or you can use the tangent inverse. I think that's also good. And I think it's very similar answer. Like the derivative. Okay, now we have actually the revolutions here. Its light here makes 4 revolutions per minute. Okay. Now 1 revolutions is, oh, maybe right here. One uh, 1 revolution is a full circle. Full circle is 2 pi. Okay. So 4 revolutions per minute means 4 multiplied by 2 pi divided by 1 minute. So we have 8 pi per minute. Oh, 8 pi radian, sorry. Because it's in radian. Okay. Now the question is asking how fast is the beam along the shoreline when it is 1 kilometer from P. So this x is, let's say at x equal 1, what is happened? So our tangent theta is 1 over 3. So what will happen with the secant? If you remember the trigonometric, I think this is also good for you. And then multiply all with 1 over cos squared theta. Yeah, you can get this two expression here that is really helpful for you in your calculus life, mathematics, advanced mathematics, engineering math. This identity is pretty basic. Okay. Why I'm doing this? Because actually I forget how I get the tangent and secant, so I need to write this. Okay, and then I will put that secant squared will be tangent theta squared. Let me write. This will be 1 over 3 plus 1. Or we can say this is 1 over 9 plus 9. So it's 10 over 9. Okay. So we are going to have dx over dt is 3, 10 over 9, and then 8 pi. It's 80 over 3 pi kilometer per minute. Okay. That will be our answer. Okay. Maybe any questions? I think for more example or for more questions, I can let your teaching assistant assist you and maybe help you with some questions. And also, do you have any, maybe if you have any trouble, or maybe maybe feedback for your teaching assistant, please let me know. Okay, you can tell me by email, or maybe just chat through the chat box now if you want to, like, maybe what do you think of the TA? Is it okay? Is it fine? Or maybe your TA is not helpful? Just let me know, okay? Because I need to also check the progress on the teaching assistant. And also, if you have maybe feedback on me, and then maybe you want to talk through your teaching assistant, you can do that also. So you can check with your teaching assistant, and then maybe you can give some feedback, and then your teaching assistant will talk to me on how they are doing. Okay. Maybe which part you are maybe not familiar, or maybe not really understand, and we can take some review. Or maybe if we don't have time to review in class, I will maybe make another additional video for you to watch on the other outside the class hour. Okay. uh, yeah, we can do that also. Okay, we can move on now. Okay, let me go. So the next will be, it's called the linear approximations. Okay, this. Oh, okay, okay. You mean the first one, right? Okay, let me. This one, right? The plane. Okay. 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 Let's continue. Oh yeah. Any other questions? The other? Okay. If not, then yeah. Let's move on from this section to new sections called the linear approximation. This is in uh sorry 3.10. If you check the textbook, it's 3.10. And by the way, we have 3.11, but we will skip this. This is the hyperbolic function. I hope you can study by yourself, but I will not include in this semester. In the exam, I will not include the hyperbolic functions, because I think now is already too much, and hyperbolic functions is basically have similar property with the trigonometric, although it's different, but it has similar property with trigonometric functions, especially the derivatives part of the hyperbolic. So I think I will just skip it for now. Okay, linear approximations. Okay. So this is, I believe, one of the example when you have when you are applying your calculus with some applications. Okay, so if you want to, for example, in our case here, approximation. So we are going to evaluate some value that is maybe really complicated, and then we can take some approach with a calculus. And in some part, like when you draw the, I'm not sure in because I think you don't really have laboratory for like physics, or maybe if you have, maybe if they prepare some video for you, or maybe you find out on your own. If you are going to analyze some data set, like from data set, you have maybe some points like that. You know that there is something called regression. Regressions means that you are making, usually you take the linear regressions, the easy one. So from this point, all random point, you take some line that is actually, if you look at the distance in between those points, the distance from the point to the line, it's not too far. It's still considered small. And we take this and we have another line equation here, right? And approximately, we are taking this into line equations from the point. Okay, similar idea, but a little bit different way. We can also approach a linear equations through a curve. Okay, from a curve. Okay. Let's say we are having. Let me write here first. So we have y equal f of x. This is just a random curve. Okay, and at x equal a, we can take the first derivative. Okay, at x equal a, we can write as f prime a, and we can take as limit approach, right? Let me write this form here. Okay, we can take this form. Okay, I will choose this form because of our section here will be dealing with the linear equations for, because we have two limit, right? We can have this. But I will take the second one here because we are dealing with the, I think, more considerably this one. Okay. If we are looking at our curve, at x equal a, okay, at x equal a, like for example here, this is a. Okay, at x equal a, we are going to have a tangent line. Okay, this is a tangent line. Or in here, you can see that we are making the tangent line in terms of L. I will tell you later what is L. This is our curve. Okay. If we are going to observe our tangent line and our curve, let's start from the more outside here. We have really a gap, right? Some distance from the curve to the tangent line. And then we are going to look at here. Also, we still have a gap, but it's much closer. And then you see here still a gap, but it's going to really close until you are going to see here. I think in your screen right now, or in your smartphone screen or laptop screen, you will notice that if I mark this and this, it seems that the curve and the tangent line, it's the same. It seems in our eyes, right? And because you see there is some pixelated like you see like that. Okay, because of the restriction or the limitations of the pixels, we may notice that this gap here, or there's no gap in between the curve and the tangent line. So what does that tell us? This tells us that f prime at x near a, we can have f prime a is actually, or not equal, is pretty much similar or approximately is equal with this. Okay. Or to be precise, if you want to look more detail, if you take this as a triangle there, this is a delta y, delta x, which is our delta here, right? Okay. So we can take this and solve. Okay, solve. Let's solve for f of x. So we will have f of x minus f of a is equal f prime a x minus a. Let's take this approximately. We can have f of x is approximately f of a plus f prime a x minus a. So we can approach f of x with f of a plus derivative of a and then multiply with the dx. Okay. Okay, it is from this form here. I think this form is quite powerful. Not powerful, it's maybe helpful because it will relate this problem with the chapter 4 and also the some method. Okay, I will show you the method later. Okay, this we call approximations. Okay, approximation. So this L of x here is called the linearization, which we can take the equations and make line equations, which is this, which is pretty similar with our approximations. But this is, we are going to have a line equation. You have some equations there, functions, right? While approximations, you are dealing with by an approximation, you are dealing with the x. X is this is the unknown value. A is usually known value. Okay. Maybe giving you some example on how we apply okay, for example, okay, if I want to calculate 9.06, okay. Of course, if you have a calculator, you can do directly. You can calculate directly square root of 9.06. You will get some number, right? So if you have a calculator, you can check with your calculator what is the answer. Well, I will show you that using our calculus and by linear approximation, we can simply calculate this with some simple calculation and we will get the answer. Okay, so first, in linear approximations, if you have this kind of question, first find find the functions. Okay, I think the suitable function for this one will be square root of x, right? So the x is 9.06. The second thing is find a. A should be something that easy to be calculated using the functions. So because f, let's say f of a should be like that, right? And remember that x is near a. So we need to find a that is easy to be square root. Okay? And I think that is 9. So choose a is equal to 9 so that we can have f of a is 3. Okay? Okay. Now find the first derivative. This is just that. And then put in a. We have 1 over 6. Okay. And then we can have f 9.06 approximate the fa is 3 plus 1 over 6 and then the delta. 9.06 minus 9 is 0.06. This is approximately or maybe f 3.01. If we want to check and multiply this, will be getting 90601. Up until here is the same as our original value. So we are, I think, close to that value. And you will notice that the last two number, if you compare with the results, this can be or it can determining the error, or you can also see from here the last decimals here. Probably it will be critical on your error. Okay? How much you are correct from the real answer. And the more you have, like maybe you have results probably 906 and then 0.00001. I think this is better than this, right? Better than 0.1. It has more zero. So which means it is in terms of error, it's less error than the previous one. Yeah, but anyway, the way you take the calculus and then apply it into linear approximations, this is one way to apply a calculus. And I think in some long calculations, this can be really helpful, really helpful. Okay, while you are still writing this, the next slide I will move to chapter 4. There is a section in chapter 4. I think it's still related to this method, the linear approximation method. And I think I can show you now because if I show you later, you will forget about the linear approximation. So I think I will show you now so that you can take notes that it's all connected. Okay, it's all connected. So this is linear approximations. Okay, I hope you get the idea here. Okay, let's take some few minutes if you want to take some notes. Okay. Let's move to the next slide. Okay, let me draw just a random function. Okay, that's just like that. And then I will make a tangent line, maybe here. Okay, maybe here. Okay. Tangent line is at this point here. Okay. Let's say this is our A, like the previous one. Let's say this is y equal f of x. Okay. And this is, let's say this is our tangent line. Okay. Okay. Now, if I have this this f of x, and this f of x is crossing the x-axis, crossing this point here, which means this is our root, right? Our root of the function, or we call also the zeros, right? The one that make the function 0. Okay. So at this point here, f of x is 0, right? Okay. Okay, let me write the terms from the previous slide. You have f prime a. So when x is near a, you can approximate with this calculations, right? Okay. Now, when f of x is 0, so when f of x is 0, we can have these expressions. So if we want to check whether we are going to find the 0 or the root, we can take this x minus a here, and this will be resulting with these expressions now. Or we can take this x, this a, and then minus. Okay. So what is actually this x means? This x here. This x is actually when you have a, okay, so you have a here, right? So this is a f of a. And then you have the f prime. The f prime is the tangent line, and it's crossing this, right? So this is actually our x. But interestingly, it's not our root, right? It's not our 0. We still have this distance. We still have gap here, right? And we want to find the root. We want to find how we can find the root. Then we can use this x. We can use this x. Take this here. And then we take the tangent line. Now it's closer. Now it's closer. Okay? Now it's here. It's getting closer with our root. And then do the same thing. Take this, take the tangent line, and I think it's really, really close now. Right? This method is called the Newton's method. And how to find the x, another x here from here? So we have x. Okay. Usually in Newton's method, we are not using a, but we are using, it's called the x0. This will be x1, x1. And then if you want to look for the another x, x2, you just change this to x1. Maybe change all with x0. Okay. And then if you want to look more, maybe it's not close enough, you think that you need to do one more time, you can still do it. And of course, to do all of this, you need calculator, right? Because there will be a lot of calculations. Maybe you need to take until x7, x8, or x20. I think 20 is too much. Maybe x7 or x8, or maybe. So this will be on the chapter 4. Chapter 4, I think 4 point something. I forgot which part, but that's called the Newton's method. So what I want to show here is that the principles behind this and the linear approximations is same principles. Just take some difference here and there. In Newton's method, you need to find the x. In the linear approximation, you need to find the function itself. Okay, I hope you get my point. Okay? You get my point here. And the whole chapter 4 is actually also related to the linear approximations. It's related to this expression here. I will show you later, okay, in chapter 4. So what I want to show you is don't take calculus in parts. Okay, so one part, one part, one part. The calculus is one system, so you need to understand the whole concept. If you want understand maybe partially, you will miss something in other part, and you will be mixed and you'll be confused. Okay, so you need to take all the things, and then we need to step by step uh, walking through, and we can see how the story is, right? Okay, like when you watch movie and you don't understand the really important part at the beginning, you will not you will feel like I don't understand the movie at all because it seems you are losing something. Okay, so that's how you deal with calculus. Okay, that's just um just a note for the calculus. And in chapter 3, actually, oh, one more thing. Okay, one more thing uh, in the chapter 3, there is something called differentials. I think I mentioned a few times, but not really in a long part. So differentials. Okay. This is just an additional note for chapter 3. Okay, I hope this part can be finished now. Okay, any questions first? Any questions? Okay, if not, I will going back to Newton's method later, the Newton's method later. So we are going to look for here. I have this graph now. Okay, remember that when you have the tangent line, you want to find the first derivative. You are having the dy dx is equal with f prime x, right? Well, you can rewrite this in terms of dy equal f prime x dx. Okay. This is we call the differentials notations here. So when we have y equal f of x, we say that f differentiable, and this will be depends on x, right? And dx is dependent, independent variable. So it can be given any real number. And then dy means it depends on dx. Not only dx, depends on x and dx. If you see geometrically, what this differentials means is, you see, notice that you have x and then some delta here. Say the distance is delta x. And you notice that from the linear approximations also, you have a gap here, right? A gap. And if you take the PR and look at the PRS, the triangle PRS, you will notice that you have a longer dy, right? A long dy here. Compare with the curve itself, the delta from QS. So if we can write the delta, this is F right? This is the change in y is fx plus delta x minus of f of x. Okay. Okay. So dy, this represent amount that tangent line rises or falls. Where the delta y, this is represent amount that curve y equal f of x rise or falls by when x is changing, by dx. Okay. Yeah, I think from this part also here, the geometry part here, I hope you get the point. Okay. So the point is actually this we call this differentials. So if you have an equations and it is start with d something equal blah 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 d blah 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 d, we call this equations differentials. Okay. The meaning, okay, in the simple words, if you have change in x, you will also have change in y, because y is related to the x, because y is a function of x. Okay. And you also can see here this f prime is also changing when x is changing, right? And we can also use differentials in terms of some calculations. So, example. Let's say we have a functions like that. And x changes from 2 to 2.05. Okay. If we take f2, this will be 8 plus 4, 12 minus 4, 8 plus 1, so it's 9. And if you would like to check 2.05, you can check the calculator, but just let me just give you the answer. 9717625. If you have the delta y, so this will resulting this difference. This is 7177625. Okay. If you have dy, in terms of dy, this will be f prime x dx. Or this will be 3x squared plus 2x min 2 dx. Okay. When dx is 0.05, dy becomes this is 0.05. And you can calculate much more easy in this equation here. So 4, 3, 12, 14, 005 is 14 multiplied with this should be 7, 0.7. And I think it's maybe close, right? Close number. Yeah, that's how you look the differentials. Okay, so usually you can take the differentials and compute in terms of the dy and dx. Okay. Well, actually, it's not really that different from our linear approximations. It's just the terms that is the different. Okay, we are using the differential. The terms, if we are using the linear approximations, is actually quite similar. It is quite similar. We just need to determine which one is x, which one is which one is a. Okay. Any questions? Okay. If not, let me check. Okay. Yeah, we can, I think, start to move to chapter 4, but I think I will just finish up until here. I want to start chapter 4 with some physics problem that you are probably familiar with. Okay. Let me just write the problem first. And yeah, let me just write the problem first. you have a functions. This is functions of positions, like in physics. Uh, you have t evaluated from 0 to 5 seconds. And the questions asked is average velocity and then average speed. So why I want to start from this, because I want to show you in some applications first on how you are looking at these two questions. Okay, we will continue from this part of this physics problem next Monday. And this will relate to our chapter 4, okay? This will relate to our chapter 4. So T is in meter and S in, T is seconds. And ST this meter, this second. But if you have, if you remember how you can maybe try to solve and find average velocity, average speed, okay? And I think this is an easy problem in physics. I hope, right? Okay, if there's no questions, you're going to work on our feedback. And the feedback is actually, I'm preparing the related rates. So I hope we have much time. Let me stop the presentation for a while. Let me check first whether it has. Okay, I think. Yeah, I think should be enough. Okay, so yeah, hopefully you can join the feedback and maybe preparing some paper and pen. Okay. Okay, so we have around almost 40, I think 40 students. I hope you guys can join, okay? And use your real name and include your student ID. Okay. Because I think I also want to consider any one of you who are joining the feedback time, not only the winner, okay, but also the one who joined. Okay, because I think I respect you and appreciate you for joining. Let's start. Okay, any more students want to join? Okay, we'll start. 3, 2, 1. I'm giving you around 3 minutes 30 seconds. So a Ferris wheel has a radius of 10 meter. I hope you understand what's Ferris wheel. Okay. Usually, if you are going to amusement park, you will see the one that are moving, okay, and you will get into some height, right? Okay, I hope the time is enough. But I think, is it too short, right? Or no? So one revolution is one circle, 2 pi. So at least you get the radian per minute for the rotation. And it's asking how fast is a rider rising. So when it's going up, it has certain height, and that height over dt. Okay, that the question. And this is just, I would just want to know how long you can take the quiz. Okay, of course this will be my consideration when I preparing an exam. So the answer should be something something pi, because it has the pi for from the radian, right? Okay, around 1 minute. If the time too short, then maybe the question is too difficult to make it in this small quiz. Okay, around 35. Around 20. Okay, a random answer. Time's up. I hope you get the correct answer. Oh, good. Yeah, it's 8 or 8 pi. Oh, you wrote with meter per minute. Okay. Okay. Should be just 8 or 8 pi if you like. Okay, let's go for the next question. Okay, let's start. 3, 2, 1. Okay, 3 minutes. Is it too short? I hope enough. It's similar with the question we had in the example. So if you have notes, you can check your notes how to do this. Yeah, the the plane and then the radar. This is similar, but this is just a telescope, not radar. But the questions is similar. So you want to asking the horizontal direction, how fast the plane is traveling. So if your distance is x, that means dx over dt, or yeah, the distance. Okay, around 1 minute. Okay, I hope you get it right. Okay, sorry if it is these two questions is the time is too short. Okay, around 20 minutes. At 20 seconds. 15. Okay. 10 seconds. Okay, just I think random answer. No time left. Oh, okay. Okay. Yeah, I think most of you, some of you did a good job. Okay. Oh, okay. Yeah, congratulations for the winner. Okay, so this will be the end of our course. So see you next Monday. We will move to chapter 4. So chapter 3 is finished. So 1 or 2 weeks later, you need to be prepared for another quiz. And the third week or fourth week will be the midterm. Okay. Hopefully, I can finish the chapter 4 by that time. Okay, that's the end of our course. Okay. Yeah. You're welcome. You're welcome. Yeah. Thank you for coming too. Sure. Thank you for joining the quiz too. Okay.